All right, so after kind of doing everything with second order equations, which is really all you need to understand, applying it to higher order equations, homogeneous equations, is very simple. Again, it's all about the characteristic polynomial and finding the roots, and we can use computers to do this in most cases. If you read through the notes, you'll see that I made some comments. Some polynomials just can't be factored by our techniques that we understand, but many can be. So again, from a textbook point of view, textbooks are going to give you problems which are possible to solve. They're not going to give you the impossible ones to solve. But anyways, let's look at this 8th order linear homogeneous equation with constant coefficients. So again, all we have to do to find the solution to this homogeneous equation is find the roots of the characteristic polynomial. So we just changed derivatives to powers of a numerical variable, which we're calling r. So y to the 8th becomes r to the 8th. Y to the 8th derivative of y becomes r to the 8th. 4 times the 7th derivative of y becomes 4r to the 7th, and so on. And we're just copying the terms to give us the characteristic equation. So this is an 8th degree polynomial equation. So it will have 8 complex number roots, but many of them, or all of them, could be real. But we won't know until we look for them. So let me just kind of go over to Wolfram alpha. All we're going to do is take this polynomial equation, this polynomial here, and we're just going to copy it into Wolfram alpha. And I just put that polynomial, just typed it directly, just used a caret for powers. You don't have to put times, you don't have to say 4 times r to the 7th, but if you did, it would still work. So when you go to Wolfram alpha, you can just use what's called factor. So it'll factor polynomials if it's possible to factor them. So once you've typed it in, your characteristic polynomial, you just hit equals, it'll process, run through the algorithms. It gives you a whole bunch of information. It tells you what your polynomial was. The first thing it gives you is just how it's factored in terms of real numbers. So in terms of real numbers, we see that r has a factor of r minus 1. It has 3 factors of r plus 3, and then it has this quadratic factor that's squared. That quadratic factor is telling us that there's 2 complex roots there. It couldn't factor it as a real. But then later on it will. And it shows you graphs, just to give you a view of this function from different scale point of views. But if you go down to farther, you get the complex factorization. So again, we see r minus 1 here, we see the r plus 3 cubed over here, and then we see those 2 complex roots. So the complex roots are 1 plus 2i and 1 minus 2i, but both of them were squared. So they're both repeating. So in this case, we have repeating complex roots and a repeating real root. But repeating roots are always dealt with in the same way. We just add powers of x to our solutions. So there's no need to factor or solve polynomial equations by hand. Just use the computer to do that. Let's go back to the notes. So I just copied this down. This is the factored form of our characteristic equation. So what do? Well, we just read off the roots. R equals 1 is a real root from this factor here. And it has a first power, so it's just to 1 power. So we get an exponential e to the 1x. So c1 e to the 1x is our first term. The next 3 terms are going to come from this repeated real root, r equals 3. So we get e to the 3x. So every term has e to the 3x in it. But since there's 3 terms, we have the first term, which is just constant times e to the 3x, plus a constant times x times e to the 3x, plus another constant times x squared times 3 e to the 3x. That's how we deal with any repeated roots. And then we have complex roots. We've got r equals 1 plus 2i, and we have r equals 1 minus 2i. Remember, all this tells us is the 1 and 2 give us the roots, tell us the 2 roots that we need, or the 2 solutions we need. The 1 goes into the exponential function as an e to the x, and the 2 gives us a sine of 2x and a cosine of 2x. So but both of these are repeated, so we have to get a cosine term. So we have e to the x, e to the 1x, that's the 1 from the 1 plus 2i, or 1 minus 2i, e to the 1x, times the cosine of 2x. But that root is repeated, so we have to add another term with x times e to the x cosine of 2x, just like we did for the 3. It's just a complex root, so we have to do it twice. The same thing for the sine terms. We get a constant times e to the x sine of 2x, because the 2 is the imaginary part of the root, the 2i that we see. And then we get a repeated root of that. That root is repeated, I should say. So we have to also add another constant times x times e to the x sine of 2x. So that we have 8 terms when we're done. Because it is an 8th degree equation, so we need a general solution of this homogeneous equation to have 8 different terms to introduce 8 constants, C1 through C8. Again, I'm just grouping these with parentheses here just so you can see where they're coming from. These 3 roots coming from the repeated root of 3, which was repeated 3 times, which we call the multiplicity of the root. And then these 2 terms here are really the cosine parts of our complex roots. Remember, we had this 1 plus 2i gives us 2 solutions, a cosine term and a sine term. So really we got, from the first occurrence, we got the cosine term here, and then the sine term here. And then because it's repeated, because there's a square in these, I'm putting the x cosine term, x e to the x cosine term, and the x e to the x sine term here. So I'm just organizing them to group the cosines together and group the sines together. It doesn't matter how you group them together. All that matters is that you have these 8 terms in your representation of the solution. Nothing else matters. The order in which you put them doesn't matter, because when you solve an initial value problem, whatever symbols you give to your constants, they will get the right values when you solve the initial value problem.